Hi, this is an introduction to group theory in Lean. It goes with section 3 of my Formalising mathematics course, and I'm not going to solve any of the sorries in this video. I'm just going to go through the basic idea of what's happening here. So how do you make groups in a dependent type theory theorem prover? Well, here's one way to do it. We're going to make a new Lean has groups already. This is one of the problems. So we can't define group is already used. So we're going to define my group. And the idea is that to make groups in Lean, a group in Lean is two pieces of information. Firstly, it's the underlying type. So we've got G, a type kicking around here. And then what we're going to do is we're going to make a new type called my group G, which is going to be the type of group structures on the type G. So G is just some bare set, if you like, if you think set theoretically. And then all the other structure, so the multiplication and the inverse function and all the axioms, they will be stored in some other term, and that term will have type my group G. So that's the idea. To make a group, you need two things. So this is a class. We haven't seen classes before. You can read about structures and classes in the course notes, but briefly what this means is we're making a new structure. A class is a kind of structure. We're making a new structure called my group G, and to make a term of that structure, a term of that type, you have to give a 1 and a multiplication and an inverse, and then proofs of all these 5 axioms. That's the idea. There's only one way to make a term of type my group G, and that's to give it 8 pieces of data. Firstly, the term which is the 1, the function which is the multiplication, the function which is the inverse, and then the proofs of these 5 axioms. That's what this boils down to. And what happens after you've just made this class is that we can do, if you want to see the whole gory details, we can do print prefix my group, and you'll be able to see all the things which Lean has made, some of which will be useless to us, but they're just there for sort of technical reasons, and some of which will be very handy. You can see all the new things that Lean has made when when this is run, when this class is constructed. So let me see if we can find some of the axioms. There we go. Look, my group.mullersock. So that's a new thing which has appeared. It's a new theorem. It's a proof. My group.mullersock is a proof because there's the colon, because it's the proof of the. This is a proposition, and that proposition, that true/false statement, says if G is a type and we have a my group, if G is a type and self is a group structure on G. Then what? Then for all A, B, and C in G, A times B times C is A times B times C. Lean omits those brackets. Multiplication by default is left associative. So Mullersock is a proof of that theorem, or the name of that axiom, depending on how you want to think about things. And there's my group.mul1 that says for all, if you have G as a type, and if you have a group structure on that type, and if A is a term of that type, then A times 1 equals A. And so on top of that, there's a whole bunch of sort of junk which we don't need to worry about. So in particular, what you need to know is that we have my group.mul1. That's now a thing. My group.mul1 says for all A in some variable that I can't work out, A times 1 is A. So what is it? Why can't Lean work out this variable? Let me just put an at in front of these things. At mygroup.mul1 means print everything. Print all the variables, even the variables that Lean is supposed to be working out by itself. So you can see what's going on. So when we add the at, here's the output here, and you can see, there we go. So you see this G, that was in squiggly brackets and that was in square brackets, and these, I've just written something about brackets. You can read about the different kinds of brackets in functions in part B of the course notes. But mygroup.mul1 is a proof that if the idea is you feed, what do you want to feed mygroup.mul1? You want to feed it an element of a group. You want to feed it A of type G, and then the moment lean sees A, it can work out everything else. It can work out G because it's the type of A, and it can find the group structure on G because it will look it up in a big table that contains these facts. So more details about that in the brackets notes in part B of the course notes. So it's kind of inconvenient having everything called mygroup.mul1 and mygroup.everything else. And so this is the point of this namespace thing here. If we that works here, but in here it will still work. But the thing you can do here is you can remove the mygroup because we're already in the namespace. So now you can just see, now we get the same answer here. So now within this namespace, we can just refer to things. Oh, I don't ever do it because there aren't any proofs here. But within this namespace, we don't have to write mygroup.mul1 or mygroup.this, that, and the other. We can just drop the mygroup part of things. And the final thing I maybe want to mention is that we're going to be training the simplifier in the next video, and the simplifier is something that does lots and lots of rewrites. The idea is you tag things with the simp attribute. There's two ways of doing that. First of all, we can define them up here and then tag them later, or later on down here you can see when we prove this lemma, we tag it with the simp attribute there. So more and more lemmas are just being tagged. It's just literally, it's like, oh, this definition has got a simp tag attached to it. You can attach tags to declarations, and the whole point of the simp tag is that they don't change things like, they don't change the behavior of the lemma or anything like that, but they mean that the simp tactic will use them. So just to give you an example of what's going on here, if I comment out this, let me just show you what this simp attribute is doing. If I comment this out, then let's do an example. We've got so here G, throughout the rest of this, beyond this point here, G is a group and A, B, C are elements of G. So an example would be, can I prove that 1 times A equals A? So right now I can easily prove that because I can just use the name of the lemma. What that will be called 1 mul A. So you see that's compiled there. Or alternatively, I could go into tactic mode. Then I could say exact 1 mul A. Let's prove that. And there we go. We're in tactic mode, so we get the goals accomplished message. But another way you might want to try and prove it is using the simplifier. So this is a new tactic that we haven't talked about before. So we try simp, and it doesn't work. This is the red underline. It says the simplify tactic failed to simplify because the simplifier doesn't know 1 mul because I commented out this line here. So if I remove this comment here, there, now you see this proof works because we've trained the simplifier to know that 1 times A is A, and one can even do, we can do things like this. There, you see the point about the simplifier is it will do lots and lots of rewrites all by itself. So that's the end of this video. In the next video I will start to prove these lemmas we have here, and we can use the simplifier to do some of the work.